Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. And Happy New Year! This is the first video on this brand new year that we started. I have to admit, for me, I'm experiencing a bit of a slow start of the year. Things will come, and new projects and new interesting videos will definitely come on the channel. The only thing that I will ask you is to just bear with me, as in this month of January and probably February as well, things will move a little bit slower than I would like to. Nevertheless, I'm coming today with a bit of an inspirational video in which I will basically show you how to create this weird looking device, if we could call him a device, that is useful when we will want to test high power supplies, such as the kind of power supplies that we will be recovering from various places and we know nothing about them. We don't know how good they are. We don't know if they are still operating at full capacity. I'm talking about, for example, server power supplies, computer power supplies, or any other form of either switch mode or linear power supplies. Especially professional ones that tend to be higher power ones, like from 500 watts upwards. In order to test those, we need to have an artificial load, and well, we might have various problems depending on the voltage that we need to test, the current that we need to test, the overall power that we need to draw from that power supply. We might have some problems because we might just not have any electronic load that can satisfy all the conditions. So we have a possibility to build something almost for free that can help us do some tests, even though it's a bit of a more, let's say, primitive solution. The solution works pretty well. This is what I'm going to show you in this video, how I took basically the three boards with resistance wire from an old bread toaster, and how I repurposed them to create this weird looking artificial load that is able to just generate heat, but it's able to, take away power from a power supply and therefore allow us to test how good that power supply is. And in general, we're going to be reiterating in this video the importance of recovering all sorts of things from wherever we can. So if you're interested in this topic, please stick around. I have quite a bit of things to show you. Before we dive deeper into today's topics, please allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you, or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need a custom metal piece for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com. The link is in the description. Thank you, PCBWay, for sponsoring this video. And now let's get back to our weird looking artificial load, and let's start talking about what I consider to be important. So I will quickly show you a fast forward video while I speak so that it's not something boring. The idea is that I've talked in the past and I will reiterate several times in the future whenever I get the chance of the importance of recovering all sorts of things instead of throwing them to the trash. The project that I am showing you today in this video is created almost completely for free from older things that I chose to keep instead of throwing them to the trash. Recently, I in the company that I work for, our boss wanted to throw away some older equipment, some old servers that were no longer useful to him, and you know, I basically convinced him not to just throw them away to the trash because they are still good and can potentially be used for certain things, not necessarily as servers, but you know, if I open them, I can definitely find nice, useful things. At least the power supplies, I knew that they were working. So I managed to convince him not to throw away these servers. I'm showing you quickly just some pictures of these kinds of servers. And I've brought them home, and yeah, I have to admit I got quite a lot of things from them. Just to name a few, like I said, the power supplies, most of them were in perfect shape. Cooling radiators, cooling fans, cables, when it comes to other specialized kind of equipment, even some boards with some analogic circuitry that I will be able to desolder and use in other projects. And honestly, I personally find useful even just the metal case of such servers, whether they're 1 rack unit, 2 rack units, 4 rack units, like this huge ass thing in here. We can definitely repurpose a lot of these things, so they are definitely not to be thrown to the trash. Something else that I chose to keep in the past, I had a bread toaster that I just didn't use anymore. I'm not a fan of, you know, eating bread that has been toasted and it's crunchy and, you know, it's dry, it's kind of solid. I'm not a fan of that. But so I chose to just disassemble that bread toaster, and I took away the small electronic circuits that he had inside. But I also decided to keep the 3 boards with resistance wire. Every bread toaster has 3 boards like the one I'm showing you here on the screen, with resistance wire that has 2 properties that are very nice for the kind of project that I'm showing you right now. One, these resistance wires can resist a lot of temperature. They are made from a very special alloy. There are actually 2 or 3 different kinds of alloy on the market, depending on where you live on the world. Well, one might be more familiar to you. Here in Europe, Cantal wire is much more common. In other parts of the world, you might use or you might find the nichrome wire. Anyhow, these are the kinds of alloys that give you wire that can resist very high temperatures. I'm not 100% sure, but I think above 1000 degrees Celsius, of course, not Fahrenheit. And at the same time, they have an electrical resistance that is pretty nice for using them as, you know, a load, as a resistor, in the place of a resistor with a certain electrical resistance, to use as a load for whatever, for an amplifier, for a power supply, for whatever things. So I decided to use, back then I decided to keep these boards I put them in a box in a drawer, and now I'm working on a new high power linear power supply, and I know that in the end I will want to be able to test that power supply, right? I'm currently in the process of remaking the secondary coils of microwave oven transformer, but that's gonna be a different topic for a different video. So of course I will want to first be able to test that transformer once I'm finishing him, and then later each stage of the power supply I will want to be able to test. I will want to have a relatively high voltage power supply, 70 volts, 10 amps. This is quite a lot of power and quite some high voltage that choosing any other electronic load would be a problem. First of all, because I don't have such an electronic load, I will need to design one, and yeah, it would be a problem for for a whole number of reasons. It would be a lot easier to just take this kind of wire that has good enough resistance for what we need and can resist high temperatures, and you know, use that as a load. The extra advantage is that in a wire you can insert direct current or alternative current, it doesn't matter. So you're not limited to direct current like in most electronic loads out there on the market you are. Okay, so basically this is at the core of my device. Put device in quotation marks because it's not a true device, right? So I used these three wire boards. They are perfect because they are made from something that looks like mica foil, a pretty large mica foil that can again resist high temperatures but is not an electrical conductor. And on top of this this foil, like we see in the image, they have wound this resistance wire. Okay, I have found that from one end to the other, each board has about 17 or 18 ohms of electrical resistance. Of course, this tends to be a bit too much. So for the sake of flexibility and you know, being able to have smaller resistances, but at the same time distribute the electrical power across the entire surface, I have chosen to basically connect one wire, one electrical wire, to each basically to each turn of the resistance wire on the board. And this is what I'm showing you now. This is how I have created one of these three boards. The other three were identical, basically. Okay, so you have two boards that have a wire on only one side, and inside the bread toaster they are placed on the exterior, and in the middle you have this board that I'm showing you on the screen that has wire wound around both sides. Okay, and the two pieces of bread fall in between these two boards. This is the kind of project where I used almost entirely recovered materials. Okay, so these boards from the toaster, from the bread toaster, were recovered, like I said. I used some monofillar wire that I believe it's monofillar aluminum wire. They're not made of copper, which are a bit, because they are monofillar, you know, they are solid wires, so they are not so flexible. I personally didn't like them to be used in other projects, so I found them perfect to be used in this project. Now, the problem with this kind of resistance wire that the toaster has is that they are not solderable due to the nature of the alloy. This is not a solderable resistance wire, you know. I mean, I think no resistance wire is solderable, honestly. So in order to have, you know, a cable or a wire that is solderable, or that you will eventually connect to something else, be connected to this resistance wire, you have to somehow make a mechanical connection between these two. So I chose to take these monofilar aluminum wires, which came in a pair. I chose to use both wires of the pair as a single wire, but I chose to have this round shape and basically hook one of the aluminum wires to this resistance wire, and then on top of this, this is an M3 screw with a washer on the underneath, and on top of this I came with another washer and a nut, and I fixed this pretty tightly. This way the electrical connection is good enough, and we get away with not being able to solder, you know, wires on top of these other wires. What else is there to say? So the entire project is not difficult. As you expect, it's just a bit of a routine work because you have to connect so many wires together. From an electrical point of view, in the end, you get to have 3 strings of equivalent resistors, let's call them. 2 strings like this, which are the boards on the that inside the toaster, they are on the outside, and 1 string like this, which is the board on the inside. For the boards on the outside, if you choose to, you know, connect wires like this at every end of every line of wire, you will basically get about, or well, I guess it could vary from toaster to toaster, but in my case I got about 1.9 ohms of resistance, again between one point and the other on the same line. Okay, and essentially we get 9. I chose to have 10 wires connected to this very long resistance wire. So this is equivalent to having 9 resistors in series, 9 resistors of 1.9 ohms. In total we would have about 17 ohms of series resistance. And if we are to connect them so that each of these resistors is placed in parallel, we would get about 0.2 ohms. Okay, I labeled these wires with letters from the alphabet so that they are easier for me to know what is which, and then to be able to connect them together. So if we are to use, for example, one of these boards with full resistance for the entire wire, basically it's the equivalent of allowing all of these resistors to remain in series, then we would just use connector A and connector J, so the extreme ends connectors and or wires, and that would be it. If we would want to place all of these resistors in parallel, that is, if we would want to take all of these lines of wire, horizontal lines of wire, and place them in parallel, electrically speaking, okay, then we would need to connect every 2 wires together. So for example, A with Ch, with E, with J, and with E on one hand, and then B with D, with F, with H, and with J. This would be another wire. Okay, so we would connect this to whatever we would need. And here we would have this approximate 0.21 ohms of resistance, because this way we have placed all of these resistors in parallel with each other. Okay. Okay, and so from an electrical point of view, they are very, very simple. Of course, it's gonna be a bit of work to, you know, actually connect all of these wires in the end, because we will have about 27 wires in total. But this is not the kind of device that you use very oftenly. It's actually you actually use such a device quite rarely, so it shouldn't really be that big of a deal that we will have to connect together so many wires. Now, from a construction point of view, I chose brick as a foundation, if we could call it like that, because the brick has two advantages. One, she's pretty heavy, so it's a good foundation. She's gonna make sure that the entire device will remain very fixed on the surface that we will place. And two, the brick can resist high temperatures. She doesn't burn, okay, like wood, like plastic. So yeah, and also the brick is not electrical conductive. So these are three advantages that I wanted to have. So again, the brick was yet another thing that I had from the past, from trying to create some other things. Yet another thing that I got to reuse, so that this device in the end was pretty cheap, I would say, almost for free. Let me show you. Okay, so I drilled some holes in this brick to use some plastic dowels, so that I can screw some screws in those plastic dowels. I used some other copper wires to pass through the holes in these toaster boards in order to hold them together. And I screwed those copper wires down into the brick. And this is how I fixed the three toaster boards to the brick. I also needed some supports for all of these cables, because these mica boards are very fragile. So once we will attach all of these wires, which are green, for me, green and black wires, they will add quite a bit of weight. And of course, we also don't want to move the entire boards and the connections, the screws, whenever we move the cables. So I wanted to have this portion of cables somehow fixed and not movable. So I chose some narrow pieces of aluminum bands. I bent them in L shapes, okay, And I basically created these holders screwed together with yet another pair of M3 screws and nuts. And let me try to show you an image that is more that will show you a little bit better what I'm talking about. Okay, so this is a view from the top. As you can see, in extreme left and extreme right, okay, these two pairs of aluminum bands, I have placed all of these wires through them. I have also placed some plastic pieces in between these wires, just for the sake of seeing them better, which wire belongs to which board. Because on one side I have two sets of wires from the external boards. On the other side, on the right side, I actually have three sets of wires from each board. So I wanted to be able to clearly differentiate between them. So I created this sandwich that you see left and right, and then I screwed and I made sure that these aluminum corners are making a tight sandwich with all of these things, so that basically the green wires between this sandwich and the mica boards from the toaster remain constantly fixated, rigid, and they do not move no matter how much I move the wires on the outside, because again we will have to move them around to form the connections that we need to form in order to obtain the electrical resistance that we will need to obtain every time we want to test something. Okay, and in order for everything to be stiff and not to break, I needed to basically use these tricks. On top of that, on the very top of the toaster boards, I have used two copper wires to basically pass through some holes of the boards, and then bent them in U shape and squeezed them with some pliers. And this adds a bit of extra stiffness to the top of the boards, so that they cannot come closer. They cannot move and come closer to each other and potentially cause a short circuit of the resistance wire herself. Okay, so yeah, this is pretty much it in terms of the construction. It's not rocket science. It doesn't look pretty, but again, this is the kind of device that we will very rarely use. Once we will want to test something, we will pull this device out of whatever cabinet we will be storing him. We will use him, and then we will put him back. And now let me show you the quick tests that I've done earlier to show you that this is pretty good for high power supplies. So on the left we see one of such power supplies that I pulled out of a 1 rack unit server. It's not a big power supply, only 600 watts, multiple 12 volt outputs. They say 16 amps maximum on each output. Of course, testing them all at the same time will be somewhat challenging, because you will have to basically take multiple wires from this power supply and join them together. Anyway, in this quick test, I only wanted to test one of these outputs. They said 16 amps maximum. I only have 10 amps multimeters, so I made sure that my load, my toaster load, to call him like this, is enough to is correctly adjusted with all the cables correctly connected together, so that I will be getting about 10 amps of current, so that I can, you know, actually measure them with my multimeters. And this is what we see here. Let me show you the multimeter, which is about 9.6 amps, almost 10 amps. And because I could clearly feel the heat if I would put my hand close, I took a thermometer and I wanted to see, okay, so I'm inputting 12 volts, 10 amps, that's 120 watts into this rudimentary artificial load. I wanted to see how hot the wires got without actually touching them, of course. So I used the thermometer, and as we will see shortly, the thermometer shows us about 40 something degrees. Now let's say that he will actually show us less than in reality, because he hadn't managed to get to proper thermal equilibrium with the resistance wire. So let's say, okay, we maybe have 50 degrees on the wire themselves. Okay, but still it's pretty acceptable for 120 watts. This means that again, considering this resistance wire can resist quite high temperatures, this means that we will be able to input much higher amounts of power from our power supplies, and it shouldn't be a problem. Our resistance wires should not melt. They should continue to be fine. Okay. So this is pretty much it. This is the device that I've built. This is how. I've explained why. I definitely recommend having something like this if you plan to use high power supplies, and if you're not lucky enough to, you know, have a very expensive electronic load. This is something that can be created very cheaply, even for free, if you already happen to have all the ingredients. So why not? I hope you've learned something interesting in this video. Thank you very much for watching. Thank you very much to the supporters of this channel on Patreon. If you would like to support my work and download all the files for all my previous projects, there's a Patreon page in the description. If not, a like and a subscribe to the channel is free and helps the YouTube algorithm further promote my videos to other people who might enjoy what I'm creating, and inspirational videos that I'm doing, like this one over here. So thanks a lot for watching. I will see you soon in my next video. Bye bye.